In this problem, we have a Norman window, which is constructed by putting a semicircle on top of a rectangle, so that the diameter of the semicircle, which is this distance right here that I'm highlighting, equal to the width of the rectangle. We're to find the area of the largest possible Norman window, meaning the area of the semicircle and the area of the rectangle together, and it's given that the perimeter of the Norman window is 30 feet. So remember, the perimeter of an object is the distance around its exterior. So we would have to find the distance around the semicircle, and remember that the circumference of a full circle is 2 pi r, so we'll just take half of that. We'll have to take that length, add that to the height of the rectangle. I'll denote that as h. So we'll have to add on h, then we'll have to add on the width, so I'll call that w. After adding the width, we would have to add the height one more time. So an equation for the perimeter of this Norman window would be half the circumference of a circle. A full circle has a perimeter or circumference of 2 pi r units. And again, we're taking half of that since we only have half of a circle. And then add the height twice, so that would be 2h. And then you have to add the width as well. So let me simplify this a bit. This simplifies down to be just pi r plus 2h plus w, and we know that perimeter must be 30 feet, so I'm going to set it equal to 30. So let me set this equation aside. We will need it later in our discussion. The next thing that makes sense would be to find an equation for the area, since we had to find the maximum possible area of this Norman window. So as I said before, that would be the area of the circle added to the area of the rectangle. So my area formula would be, let's see, a full circle has area of pi r squared, but since we only have half of a circle, that would be 1/2 pi r squared. So that would be the area of the semicircle, 1/2 pi r squared. Let's add to that the area of the rectangle, which is obviously h times w. And our job is to maximize the area. And currently we have too many unknowns. We have r, h, and w. Somehow we have to make substitutions for either r, h, or w, two of the three, so that our equation for area is a function of one variable, not three. Now we can go back up to this equation for perimeter that we wrote earlier in the video. What I can do is pick either r, h, or w and solve for it and make a substitution into our area formula. So for example, I'm going to arbitrarily pick h, solve for h, and once I solve for h, I can substitute whatever h is equal to into the letter h in my area formula. Before I do that though, I notice I can replace w with an expression of r by simply realizing that the radius here of my semicircle is exactly half of the width, or to say it another way, the width of my rectangle is exactly twice the radius of the semicircle. So where I see w in my perimeter formula, I'm going to replace it with 2r. So that means I'd have pi r plus 2h plus, here I replace w with 2r. And now I'm going to solve this equation for one of the two variables, r or h. I'm going to choose to solve for h. So on the right side I have 30. I'm going to subtract over the pi r, and I'll subtract over the 2r. If I multiply both sides of the equation by a half, that would give me that h is 15 minus 1/2 pi r minus r. Now that I have solved for h, I can take that and substitute it in for the h in my area formula, and I would get that the area is 1/2 pi r squared plus, here's where I replace h with 15 minus 1/2 pi r minus r. Don't forget that's being multiplied by w. And I still have too many unknowns in my problem, but remember, I still know that w is equal to 2r, and then replacing w with 2r, now I only need to distribute the 2r to the three terms in the parentheses. That would give me 30r. When I multiply the 2r by the 1/2 pi r, the 1/2 and the 2 simplify down to be 1, and I'm just left with subtract pi r squared. And then finally 2r times negative r is minus 2r squared. One last thing I can do is notice that this term and this term are like terms. So since I have a half pi r squared and I'm subtracting 1 pi r squared, I can combine those terms. Since 1/2 minus 1 is negative a half, I get negative 1/2 pi r squared. And then I still have to copy the plus 30r minus 2r squared. And now I have my area of my Norman window is a function of one variable. So now I can find the maximum area by just graphing it on my calculator. So let me go to my graphing calculator, and I'm going to press y equals, type out the equation. I have to use the letter x for the radius because my graphing calculator only allows me to use x as the input variable in my y equals menu. So now I'm done typing my equation in for the area. Just make sure you realize that the letter x in my calculator represents the radius, and the output y sub 1 in my calculator represents the area. Now I have to set up a good window. If I press window, I see I'm currently in the standard window. Knowing that x in my calculator represents the radius, I have to ask myself, how small and how big can the radius be? Obviously, we want the radius to be positive, so I'm going to say it's bigger than 0. How big we make it is something I can only estimate. So we know the distance around the Norman window is 30 feet. How big r could be would be the same question as how wide could we make the Norman window? We could make an extremely short Norman window and really wide window. Obviously, the most we could use would be close to 30 feet. Imagine a scenario where your width is almost 30 feet. That would use up almost everything we have available to construct the window with. And that wouldn't even be counting the material needed to make the semicircle portion of the Norman window. But even if the width was 30 feet, which is silly, r would only be half that amount, which would be 15. So just as an exaggerated x max, I will say 15 feet. And then remember, when I do my y min and y max, y represents area. I have no idea what the area of my Norman window could be. We could play with some numbers, or if you want, you could just hit graph, and you'll notice that our window is wide enough to see the parabola, but not tall enough. This is where you could just press trace and start looking at some y values that you get out. Remember that the y represents area. So for example, if our radius was 7.5 feet, the area would be 24 square feet. And you can trace around to see how big those y values or area could get. And I'm seeing numbers in excess of 40 and 50. So I'm just going to go to my window, and hopefully 100 would just be an overestimate to the largest possible area. I will regraph it by pressing the graph key, and I notice that the graph that I'm seeing has a definite maximum here, somewhere around 4 feet for a radius. But I want to use the full accuracy of my calculator to find that maximum area. So I'm going to press second trace, press number 4 on my keypad to access the maximum feature on my calculator. As a left bound, I'm just going to type 0 in since that was my x min. And as a right bound, you can type something in like 7 or 10 or whatever your x max was in your window. But as long as you pick a point to the right of the maximum, now the calculator will be looking between x equals 0 and x equals 7. And it looked like the answer was somewhere between 4 and 5 in terms of x values. I'm going to press enter to enter my guess. Make sure that you have the word maximum sitting on the calculator. It looks like when x, or the radius of my semicircle, is 4.2 feet roughly, I will get the maximum area of the Norman window to be about 63.01 square feet. Because the question is what is the area of the largest possible Norman window, we're done with the problem. It's 63.01 square feet, or to the nearest square foot, 63 square feet. Now you need to go buy 30 feet of materials and have fun building your Norman window, and it will be the biggest Norman window that you could possibly make.